Okay, so I have the unenviable task of moderating this session. And it's a discussion panel which I think should be more like an informal conversation, not only with the audience and the panel here, but also if you're tuning in from online and the internet space, we're happy to hear from you as well. We'll get the questions relayed to us directly. For the panelists, you do need to press the speak button to speak. We have a number of questions that the committee brainstormed to sort of catalyze a fun and lively discussion. And so with that, maybe let's start off. Sort of a broad question, and I'm not going to call on the panelists. Hopefully one of or more of you volunteer to give your opinion on the particular questions. One is sort of on the topic of the near and long-term societal and economic justification for focused efforts in electrochemistry. In other words, how do we convince the funding agencies to give us some money? I think that's the question. So why? So for the panelists who I would hope would opine on this topic, what would you say is the sort of elevator pitch, or why would electrochemistry be a key area for scientists and engineers to consider in the U.S. going forward? So with that, hopefully someone can start us off on what they would view as a quick elevator pitch to your favorite funding agency.
So hi, Bill Tumas from NREL. We're basically in the midst of what's going to be a remarkable energy transformation in how we generate, how we store, and how we use energy. It's going to be, if you think about where we are right now, we've got photovoltaics and wind and renewables essentially at grid parity. They're not done yet. The car didn't stop at horse parity. The renewable energy is not going to stop at grid parity. And that we have a complex mixture of scientific, technical, economic, social, and political elements to do with that energy transformation. But one of the key messages, as you heard in a number of talks today, is there's still a lot of room for innovation. We've come a long way, but we still have a long way to go to really get where we need to go. I would say there's a national security imperative as well. The U.S. can't just be at the front of innovation in this energy transformation. It has to be at the front of the economic aspects of this transformation, from manufacturing to deployment. And I think the whole thing really centers around that we did a transformation from animal horsepower and wood to fossil energy. And we're going to see a next transformation to basically a deep electrification, where we're not going to just electrify our cars, we're going to electrify our buildings, and as we heard today, we have the opportunity to electrify our industry. And clearly, we could see that there's going to be basically a solid-state, software-driven, on-demand, renewable energy and storage system that's going to be cost-competitive. And doing that just not for our electrical use, but for our transportation, but for our industry is really important. And so imagine electricity now being the cheapest form of energy, not the most expensive. And imagine all the things we have to do to take those electrons into items of commerce, into ways to do heating, into ways to do transformation. And the only other thing I think that there's an imperative to do, and that's to actually start to create a circular economy. And as we design this next energy transformation, we need to move away from the linear concept of make, use, and throw out to really reuse. And that's not just in the plastics and the products we make. It's also in the elements that we make. Very few elements do we do a very good job of recycling. This whole idea of designing that next economy, and that's technology from the science we need to do to design to remine all of these things is going to be critical. And then we've even talked about a potential circular economy in things like carbon dioxide and other aspects of air to make items of commerce, fuel, and the like.
Brilliant.
I guess I would add to that to go to, maybe it's not the opposite side of the energy applications, to think about health sciences and health services. Obviously, electrochemistry has played a role in the life of a diabetic patient, being able to use electrochemistry to be able to test glucose in their blood. But as we go to personalized medicine and we get more comfortable with our Fitbits and our sort of monitoring capability, the idea that sort of electrochemistry is going to take us into wearable diagnostic devices and sort of wearable devices that will tell us about health and fitness.
So the point that I'd like to add is that electrochemistry is often the medium that allows people to interact with technology. In other words, we're going to have solar electricity generated, we're going to have wind, but in society, we're used to using electricity on demand, and that's a societal need. Electricity isn't generated evenly, so we're going to have electrochemistry that can help mediate that. Same thing with an electric car. We're going to have electrochemical storage to allow humans to interact with that EV effectively. So it sounds, really corny and, almost like a pun to say that electrochemistry really is at the interface of humans and technology, but it actually is, that it's often the enabling piece that allows humans to use electricity and use it effectively, because that's what we want. We want electricity, we want services, we want functioning technology on demand, and it's that ability to store electricity effectively and use it on demand and use it portably that electrochemistry enables.
And I think I'd like to add, Jeffrey Dick, UNC Chapel Hill, I'd also like to add that electroanalytical chemistry is now at a point where we're incredibly sensitive, single atoms, molecules, and nanoparticles. And so the frontier of really understanding reactivity at this single level is ours for the taking. The second point that I'd like to make, we heard some very beautiful talks today about electrosynthesis and in making different bonds. But there's also another frontier in breaking bonds, too, for environmental remediation with electrogenerated radicals.
Any other, so I think that a lot of these points are really good, and it seems like there's almost every facet of humanity can be impacted by studying electrochemistry, and it seems like it's almost self-evident. Like, I wonder, is there even a counter-argument that could be made? It seems like the asymptote of efficiency is humans sort of embracing electrochemistry, and so the funding agencies are watching. It's kind of obvious you should, fund this vigorously. And maybe if you're not convinced, we need a grassroots effort, which gets us into the next discussion topic, which is how do you educate, from the ground up? What do the various agencies, whether they be the DOE or NSF or ECS or ACS, or we even have NIH here, what do they need to know about the needs for electrochemistry training?
Well, I wanted to comment on that. We heard a very intriguing comment this morning that it might be easier to teach an electrochemist other disciplines such as material science rather than the other way around due to the inherent complexity of our discipline. And I think that means there's a race against time. We need to expose our young people to all the relevant facets and scientific disciplines that come together to form what we would consider electrochemistry. And so I think an integrated science approach that embraces the physics of electron transport, electricity and magnetism, alongside organic chemistry transformations and inorganic chemistry and redox potentials will be enabling for our young people. It's one thing to collaborate with someone else who has adjacent knowledge to you, but for our young people to have all the relevant understanding and capabilities together in their brain leads to a generation of people poised for new innovation in next generation electrochemistry. And so that's something we're trying to provide. And I think it's within our grasp to unify the educational program of our young people at the college level and even before.
So I was thinking a lot about this and thinking about, what really motivates the next generation and the next generation beyond that? And to me, it really begins with the experience that people have in graduate school, because it's the graduate students that end up being faculty at colleges and faculty at universities. And when you've experienced something as a graduate student, oftentimes you take that with you. So yes, we need to change curriculum. I'm good with that, because oftentimes I can speak to our school. Electrochemistry is taught maybe at the very tail end of freshman chemistry and then may not ever be taught again. But I think it's really that research experience that's going to drive the next generation of expertise. And I totally agree with Andrew's comment that fields need to blend at the boundaries. I think the more strictly we define things and say, that there is no overlap, I think that's a risky path to go. I think if we blend boundaries, that's oftentimes where really significant discoveries can be made.
So I think I'd take this in two parts. One, for the funding agencies, which I think was the basis of the question, clearly what's the impact, therefore what are the needs, therefore what are the challenges, and what are the approaches. You could look at just today. We heard about catalysis. We need to control everything from the microenvironment around a catalyst to get high selectivity to get efficiency. You can think about polymers. Membranes are implicit in a lot of the things that we talked about today. Maybe they weren't as explicit, but there's a whole set of polymer science and engineering that goes around that. You can think about reliability and durability, which is a major aspect here in addition to circularity. On the engineering side, scale is something that's going to be huge in some of these areas. Certainly maybe not the microarrays. That'll be scaling up by numbers as opposed to size. So reactor design, how to do the science of integration, electrically driven separations we didn't really hear a lot about today, but I think we'll hear some tomorrow. On the mechanical engineering side, materials of construction, some of the issues with thermal management. A 70% electrolyzer sounds pretty good until you realize a megawatt electrolyzer has 300 kilowatts of heat you have to deal with. And you have to clean up the water on the front end. And so it really brings me also to the electrical engineering front. We saw Tom with a really nice system today. The cell's in the middle. If the cell was free, a lot of those electrolyzers are still too expensive and have a lot of room for improvement. So there's a whole balance of plant that goes around there. There's a whole power electronics piece that goes with that. There's a whole set of, do we need transformers and rectifiers, and how many times are we going to invert as we do large-scale electrolysis? What do we actually do with the low-grade waste heat that comes out of there? And so I think we take lessons from other places. The chemical industry, I learned when I was at DuPont, there's a reactor in the middle, and the whole plant is the front end and the back end. And the reactor in the middle is really important. But that whole other part of the balance of plant is going to be really important for these large-scale electrolysis systems. Take the lessons from photovoltaics. It was the supply chain and all the balance of plant, as well as a lot of the permitting and installation, that drove down the cost of photovoltaics, in addition to the advances in the materials and science of the cell itself. And then if we're going to make a lot of any of these, what's the science of manufacturing? How do we take synthesis science and turn that into processing and manufacturing science?
So you gave a large number of things that students need to learn. And I would say in the average U.S. university, we probably either teach an electrochemistry graduate course or we teach an electrochemical engineering graduate course. And occasionally we might teach both. But I think, we need to learn from, other countries that may actually have entire degree programs in electrochemistry, to be able to think about the fact that everything you said is fantastic, but it's not going to fit in a semester course or even 2 semesters of coursework.
These are all such great points. I'll add to it. I have a couple of thoughts on just education in general, electrochemistry. One is shovel-ready ideas. One's longer term. In terms of kind of shovel-ready ideas, I'm really excited given the wave of new faculty that are emerging from labs that did their graduate work, I should say, in electrochemical technologies one way or the other, and many of them are, in fact, introducing these courses, and we need a lot more and perhaps dedicated programs, and that's something that can be done in the near term and hopefully continues to grow. The other angle panel was that, given how pervasive electrochemical technologies have been in our society for many years, there's one thing that I'm seeing today that I've never seen before, and that is really a battery-powered vehicle has changed everybody's perception of electrochemistry. And it's really weird because we've been, everyone carries around smartphones, and we all hold them to our ear and we talk, and without a really good battery, that is a useless technology. And so I really enjoy teaching students how a lithium-ion battery actually works, so they know where the lithium is moving or that it is even moving whenever they're actually talking on their cell phones. And for some reason, but their excitement was dominated by the cool features of the smartphone, whereas when it comes to a vehicle, they're seeing it differently. They're seeing the battery is really the big enabler there, and that's wonderful. Let's leverage that. And my point with that is that now that their attention is captivated, how can we take all the courses that we teach at the undergraduate level, and thermodynamics is thermodynamics, whether it's conventional chemical thermodynamics or electrochemical thermodynamics, exactly the same thermodynamics. It's just a different formalism. And so why can't we just teach that together? Reaction kinetics and electrochemical reaction kinetics are exactly the same kinetics. They're just, the rate expressions are the same. They have a few different terms. We can teach that unified. Separations. Transport is transport. And so I think there's also an opportunity, shovel-ready idea of how to integrate electrochemical concepts already into existing curricula to teach thermo and transport, et cetera, and just really teaching them both so they're prepared. And I think that we have batteries serve as that vehicle, in this case, no pun intended, to help teach that. One last comment, that's short-term shovel-ready. On the longer term, I'm really excited to say that I'm seeing at the university level, I'm hearing a lot of universities really asking the question, what does an undergraduate education, how should a university operate in 2030 or 2040? And I think I'll speak for myself, but probably many in the room agree with me on this. I feel like my undergraduate education was more teaching chemical engineering of the last 50 years as opposed to necessarily teaching chemical engineering for the next 50 years. And I think universities are broadly saying, society is changing, society is evolving. How do we evolve with it? How do we provide the best experience for our students? And my point in all of this is the iron is hot and getting hotter and hotter, in that as the whole framework of what a university is evolving, we should be thinking about that, and so that we can not skate to where the puck is, but skate to where the puck is going to be, and we can phase match everything we're talking about with that future of universities.
Good. Thank you, Tom. That was a good lead into what I wanted to say. I think that students come to university interested in learning what they want to learn, pursuing their own curiosity and interests. And so telling them, here's a series of textbooks, and once you master what's in there, then you can do something interesting. This is not a good match to today's student that can access so many things on the internet. And they come in with a great passion to improve the world. And so electrochemistry can satisfy both of those needs. But I think that a robust course leading students into the laboratory at the earliest possible stage is an exciting development. We have always had undergraduate research. This does not sound like something new, but the idea of coaching students on how to read a journal article and how to work in a team and ethics of research and what are the most promising challenges of today, and then how to funnel down from an area to an interest to a topic to your exact bench research problem, and then to funnel back out again and understand its importance. These are the things that can empower our students to go straight from the classroom into the laboratory, and then we find that they will be more motivated to return to the classroom because they realize there's a subset of knowledge they need that will enhance their ability to perform research. And so integrating research with the undergraduate coursework experience, I think, will be a growing trend in the coming years, and that's something to be applauded and supported.
And just to add to that, I think a lot of institutions are trying to get to that point. At Carolina, within the next 5 years, we want every one of our undergraduates to have had research experience. And electrochemistry has a tremendous benefit in that the activation barrier in terms of cost to do interesting experiments is quite low. In my graduate electrochemistry course, I have my students build their own potentiostats, and some of them are screening different materials for electrocatalyst discovery for all less than about $60 per student. And so these are, I think, rather small line items to put in grants for funding agencies moving forward for all of us.
I would just add that we also, if you look at a lot of fields and where the impacts have come from, it's a lot of people from other disciplines addressing problems in electrochemistry as opposed to being experts in electrochemistry to have impact. And I think this is an area where, there's still plenty of room for electrochemistry to meet more material scientists. They don't even have to both be experts in each other's field. We see the power of team science, and I think teaching students team science now is really important. The power of big tools, whether it's big data, whether it's artificial intelligence, whether it's first principle theory. Maybe Esther wants to comment on some of our impressive beamlines and the power that they can do, as she showed in her talk. And so this idea of it's not just single PI science, although there's still lots of places for that, but there's a lot of multidisciplinary approaches, and getting people who can have an impact up to enough of a speed so they can have an impact, as opposed to not everybody has to do Tafel plots every day to solve a problem in electrochemistry.
Bill, thanks, because I do want to pick up on the idea of team science. Probably, certainly most people of my generation, when we went through graduate school, it was kind of like one student, one project, one PI. That's kind of how the world worked. But when we look at the scope of the problems that are being solved today and the way big problems are really being addressed, it is through team science, it is through collaboration, it is through multidisciplinary approaches. And I think exposing students to that and letting them understand that there's something beyond, their, strict, siloed project in terms of science, I think is very powerful. I mean, that's how we've been approaching things. I can tell you universities are pretty sometimes conservative, so not everybody buys into the notion of team science and collaborative science. But I think it's the way the world is moving, and I think it's important for students to participate with that.
Well, these are all extraordinary points. And what struck me was Jeff mentioned the $60 apparatus. And I think that is a great segue to the next topic, which is if you could dream, what types of devices would you ask for the companies out there who are maybe doing due diligence at this very moment watching? What would you want them to invent, whether it's a new analytical instrument or an instrument that would be useful for a dedicated technique? What is missing from your equipment repertoire at the moment, no matter what field you're in, that you feel could fill a huge gap in the area of electrochemistry?
Could I interrupt before you say that, before we leave education?
Yeah. Oh, yeah, let's stay on education for a moment.
So,
and then we'll get to equipment. Yeah.
Sorry, I'm a little under the weather here, but it's been my great concern over many years, the lack of rigorous teaching of electrochemistry in this country. If you look around, how many departments, top departments or not so top departments, offer what I would consider rigorous training in electrochemistry, and there's probably very few. There's also the sense that yes, we have one electrochemist in our department. We have that covered. When was the last time you ever heard that about PChem or organic chemistry? Never, right? How many departments have more than one electrochemist? I don't think there's any in this country, right? Or very few. Yeah. So Illinois, very, very few that I would consider having been rigorously trained. And so right now electrochemistry is popular because there's money in it. 30 years ago, when there was no money, nobody gave a hoot about electrochemistry.
I take a little exception. I think that electrochemistry is popular because people see the impact of it. And I'm worried. I mean, I sat through a Baran and Faulkner course long before I thought how important electrochemistry was, and it was just another aspect of physical chemistry and trying to learn it. And I think getting this impact and relevance out earlier, and then people do the fundamentals. So Carl Koval is a retired professor from CU Boulder, and he's been interfacing with NREL. He's teaching out of Baran Faulkner, just a casual course, a weekly course. We had to move it to the cafe because 100 people signed up for that course. People who probably have never taken electrochemistry, may not be able to balance a freshman equation, wanted to understand what electrochemistry was about.
Well, he was rigorously trained by Fred Anson.
Yeah, I understand, but I think it's the impact, not just the money is where
but
I think the impact's well understood now.
It helps.
No argument.
Right, and so how do we encourage chemistry departments to actually hire electrochemists, more than one?
Thanks, Professor Bruno. I think that if you have questions, by the way, you got to get my attention. I'm sorry, I didn't know.
Can I take it from here?
Yep, great.
Okay. As somebody who was rigorously trained, chemistry departments are not by default home for electrochemistry only. Electrochemistry is inherently interdisciplinary science. When I arrived last October at University of California, Irvine, I met 18 colleagues who were electrochemists. 13 of them were in engineering. In 1 month, we created the first rigorous graduate curriculum in electrochemistry, consisting of 8 engineering graduate classes. 2 are in line to come. 2 undergraduate shared topical electives, and there is 1 very good electrochemistry class taught in the chemistry department based on Barth and Faulkner, still with the wrong assignments of polarity. So, as an expatriate European and an engineer, I can tell you that when you work with electrical engineers after you, you need to know how to assign the polarities. Because those guys totally get messed up if you mess up. So now, going back to the curriculum. We have 2 sets of educational problems. And actually, Tom was the one to touch on that because he's a fellow chemical engineer. There is a problem of patching up what you have with the art that you have in hand something and do something immediately, and there is a strategy. And the strategy is how to create a competitive electrochemical curriculum that will put us apart with places like Grenoble, Montpellier, Poitiers, Paris Diderot, and places when people teach electrochemical engineering and electrochemistry and give degrees in it since 1903. Okay? And these are the things that we need to cope with. Majority of the comprehensive books need to be written in such a way so they will stick to each other. I'm ready to recite for you the names of the courses, and you will be saliving that they are individual courses taught by very, very well prepared professors. They will simply offer it here and there as electives every other year, but when you combine them in a University of California, Irvine, in the orientation class that is general electrochemical engineering, there are 64 students. When it comes to the sequence of fuel cell modeling class, which is 3 classes later, there are 17 students. All of them PhD students. And this is our reality. When you hook that with the so-called professional Master of Engineering initiatives that every dean wants you to do, which means you add a summer battery class and a summer corrosion class taught by a practitioner from the industry, you have a comprehensive PhD graduate program in engineering hooked up to a science course with an anchor in a Master of Engineering. And it is because the students, as you also mentioned, in the elevators are talking how cool is the next Tesla model. Because on the corner we have a hydrogen fueling station that disperses 50 tons of hydrogen a year. When I go shopping into my Iranian local store, I put my car between a Mirai and a Maserati. And that's the other reality, that the Orange County and city of Irvine has more Mirais than anybody else in this country. They all come to fuel Friday night on the university-owned station. Students are talking that they're hip. They love the Teslas. That is really what they brought them in, because the cellular phones were grabbed by electrical engineering professors who teach them apps. The cell phone is about the apps, and the Tesla is about the battery. And this is our right, and you mentioned that very correctly. For the first time in my life, I say, I'm totally agreeing with you what you said. It's unbelievable.
Wait!
Dave's
Don't
not over, Plowman.
Don't go. Maybe you could. I'm going to call you back up in a minute because you made so many great points. But maybe we'll go to the next.
Yeah, thanks. I just like to say, as someone who's done 30 years of teaching in the university, students, undergraduates in particular, are motivated because they come in and they want to save the world, right? That's what they want to do, right? And so about to 70% of them, that means they want to make money in the business school. But the other 30% who major in sciences, either it's they want to cure cancer or they want to solve whatever, there's something, the energy transition or do something like that. And I think for us, tying into that excitement and continuing to tie into that excitement is the way forward. You show people that there are opportunities, maybe by having a Mirai fueling station, maybe by having a Tesla in front of the department, which is an outstanding idea, which we will do immediately, or by showing people in undergraduate classes, and it doesn't have to be a concerted program, but it'd be nice to show them that the future comes in an electrochemical opportunity. Even in an organic class, I mean, Marty is here. I don't know. Do we teach any electrochemistry in an organic chemistry class? And I would bet the answer is probably no, or very little. And I don't mean that as a detriment or anything like that, but you might say, here's a new opportunity in organic synthesis, which I think you've demonstrated very nicely, right? Let's have some education in that way. Once you get to graduate courses and to future faculty, again, where are the opportunities? And that's what we need to show them. Here are the opportunities in electrochemistry, broadly defined. Electrosynthesis, in bioelectrochemistry, in fuel cells, in batteries. These are the places that new opportunities are arising. And if we say that in a convincing way, we'll get more and more people in there, and our job will be 80% over.
This is a great point, and maybe because there's so much lively discussion on this topic, we should forego for a moment the equipment discussion and maybe return back to your point you made before on the Renewable curriculum. Because one of the things we were going to talk about later, but maybe we should talk about it now, is what we can learn from places like Europe on the way they educate. And so that's clearly something we can learn, but where is this information? Can the curriculum you mentioned, is this something that can be found? Is a review written about this? A thing you've talked about? Is it something that's available online? Or?
It's all online.
Everything is online.
Absolutely. But in French.
But in French, okay. Is there a English equivalent to that?
It's called Southampton.
Southampton has all the notes and okay, that's very useful for.
Can I just interject? I mean,
sure.
I'm just going to throw out an idea for an opportunity, right? And so this is, speaking of where the universities are going to be in, say, 10, 20 years, one big question is online learning and what's going to happen with that. And that's definitely very dynamic, very much in flux. But let me say, if there were, say, a dozen people who are participating in this meeting online, in person, we're going to say, let's together come up with an online course that is going to be a dedicated electrochemistry course, and then, package that. And then that could be something that's shipped to every university worldwide and say, can this be integrated into your program, right? So Plowman, we just described, for instance, could that be ported online and then other people here supplement that? And that way it's not like every university on earth has to have that resource of 18 faculty, even if there's just one person who could be the shepherd or shepherdess of that particular course or program. It's others from around the globe who are participating in. So half-baked idea in full disclosure, but maybe that's something we should talk about. ECS can sponsor. Yeah.
They can host it.
Yeah, that's right. Sponsored by hosting.
So there's a question, if we can get a microphone to the gentleman.
Can I speak to the education?
Yes.
My name is Justina Wajira-Kalinowska, Adelphi University, Garden City, New York. I've been a faculty member for 15 years and teaching at mostly undergraduate institution. And knowing what I see in the classroom is students, when they're coming to the class, they have no clue what electrochemistry is. So we should start the education early on, like ACS is doing. I'm actually also a chair of the New York section in 2019 of ACS. You have to start early education of the kids. ACS is doing a great job with National Chemistry Week. We should also do this, participate together with the ACS and show many different aspects of electrochemistry right there at the beginning of the educational path. ACS will help. Besides, so this is the early on when we have to introduce students to great topics of electrochemistry. What electrochemistry is? They see a cell phone every day of their life since they're 1 or 2 years old, but they have no idea what this is. And they have definitely no idea that this is chemistry and electrochemistry behind it. And second of all, once they actually come to the university, we teach maybe one chapter at the end of the semester of electrochemistry, and that's about it. They know how to balance the electrochemical equation, but they don't know the application of it. So I really agree with the people who spoke before me that we should add the electrochemistry part to every part of chemistry: organic chemistry, physical chemistry, analytical chemistry, general chemistry. Each the topic of chemistry should have electrochemistry part in it, but not only to have a chapter of it, but also to assess on it. When I check the ACS exams, there's only one barely question on the electrochemistry out of 100 questions. So this is a very small percentage. Students say, do I have to learn that? If it's not on the exam, I don't have to learn that. And on the top of that, besides teaching assessment, there should be also practical part of it. So I encourage that Electrochemical Society and NSF would focus also on placing those students into some kind of a different labs, not only academic labs, but also industrial labs, industrial collaboration, so students can know, okay, whatever I learn in class, I can apply, I can use, it's useful, and also I'm going to make money later on. This is creating jobs. I'm not learning because it's fun, I'm learning because I can live on this. So, for example, for the last 3 years, I've been actually taking my students to the University of Warsaw in Poland. This was actually funded by the NSF grant called IRES, which was a very successful grant for me. I was able to take with me about 15 students in the past 3 years to Poland. They came back and they all want to go to grad school and study material science. I feel that this is success. They don't no longer want to be medical doctors only. So I think more of the opportunity that is given to undergraduate students, because truly you're not going to find them at grad school and interest them at that point. You have to start early on when we feed them to the universities. And we have a lot of different undergraduate universities in U.S. Besides also, why do we always have to take students one way only? So we, about 60 to 70% of the grad students are international. Where is the U.S. workforce? So I'm lucky. I came also from Poland, and I got a job here. Why? Because we didn't have enough people who were educated at this point here. So why don't we take an opportunity also otherwise? Why don't we send our students out? They come back, they're so much more mature, and they see the global aspect of this also. Thank you.
Some really super points there. Yeah, thank you.
Hello, my name is Arsalan. I'm from Florida Gulf Coast University, another PUI primary undergrad institution. So I have a question for panelists, and I'm looking for a solution, not a long answer, very focused, concise solution, please. So I am an ionic liquid guy. I make ionic liquids, and so all my undergraduate students, they know about the batteries because they work with the electrolytes. I'm not an electrochemist. So I teach electrosynthesis of field in my advanced organic chemistry class. When I did my undergrad, electrochemistry was mandatory for undergrads, but here it's not like that. After Nobel Prize this year, well-deserved Nobel Prize this year, finally after a long time. So a lot of students come to me and said, if I want to get my PhD in electrochemistry, what should I do? And normally when they apply, they don't get a good response because they don't have a related research experience. So I encourage some of them to go to that NSF summer research program. But that one was not successful either because my students, they do material characterization or synthesis of organic materials. It's really difficult to convince an engineer or electrochemist to take my student and get a PhD from. What is the solution for my problem? Thank you.
To try to recap your problem, I think you're saying you have an undergraduate institution where the research opportunities on site are few, how can students go to graduate school from your school? Is that the question?
How can they go to graduate school, do electrochemistry?
Yes.
We don't have electrochemistry.
Yes.
We have one instructor teaching 4 courses.
Right. I think that the key that would be the lowest price of entry would be to have an undergraduate research program that centers around extremely inexpensive apparatus. And at this point, the cheapest thing is to have theoretical research, that you can have running quantum mechanics programs for less than $100, on a desktop machine, and students can explore real materials and can explore electrochemical transformations, and you can have aqueous electrochemical cells set up in a teaching lab, and students can do projects at first where they reproduce results from published papers and then have an offshoot that may be publishable. But I think my experience is that graduate schools take notice of any research spark, that if there's an advisor who writes a letter saying the student showed promise in research, even if it is not leading to a publication, it will still be much more than nothing. And that could be a jumping off point, and then the NSF REU would augment that portfolio further.
That's what I did. Just so you know. I went to an undergrad institution. There was no...
Maybe the microphone, because I don't think the people online can hear. Yeah.
I went to a primarily undergrad institution. There's no graduate, research program there or anything. And I did computational chemistry as an undergrad, and I got a paper out. What's that? Did you go to REU? No, I didn't. I had some good professors who were medicinal chemists, and we did kind of a physical organic study. And then I worked for a couple of years, and then I went to grad school. But I will point out that undergrad publication was important for everything moving forward.
So,
I'm going to send my students to you guys.
So, I was going to say absolutely, because to me, it's very, very, very few students, graduate students, who join our research group who have direct research experience that's relevant to what we do. So the vast majority of students don't, and I totally agree with Andrew that if a student shows interest, if they show capability, even if they've done something different, if they're really interested in what we're doing, that's great. I don't think there's a prerequisite that they have to have undergraduate research experience directly relevant to graduate school. In fact, I think that's often not the case. But if they show interest in research, if they show interest in electrochemistry, if they're generally a capable, strong student, I'm really optimistic about their future and their ability to get into a program that would be important to them.
The reason I asked this question, my 19 years old undergrad, but one on one to teacher, you didn't get any. You got a lot of graduate students, I'm not rejected everything.
We have a little bit of a line on comments. I don't know if the gentleman up there was before, but since you're standing, if you want to go, and then. Oh, sorry, Tom.
Yeah, no, I just want to add one thing. I mean, I think the comments that were raised, I just want to broaden that out, and I think this is there's a broader challenge that we should all be thinking about, and that is diversity in our field. And what you're describing is basically pathways. There's diversity of different backgrounds, and some students are not afforded the same opportunities that other students are, which allows for a selection bias or enables a selection bias at the graduate level, which is very unfortunate. And that's one path. But there's other paths. It could be based on gender. It could be based on where they were born. It could be based on ethnicity. It can be based on lots of different things. And clearly, we need to address that more broadly. So I think the point that you were making of disadvantaged students that aren't going to have the same chances of others, I think we need to think more deeply about that and come up with solutions to that broader problem.
So I think a lot of the societies now are having very interdisciplinary symposiums, and you might want to reach out to people who are attending those symposiums. So the Electrochemical Society has a 2 or 3 day symposium every 2 years on ionic liquids and electrochemistry. And I think looking at those invited speakers and sending an email and saying, do you have summer undergraduate research opportunities. My students know about ionic liquids, but they don't know about electrochemistry, and they want to get that experience. May help them, and may help you make some connections as well.
Hi, thank you. I'm Christopher Januzzi. I'm the Executive Director of the Electrochemical Society, and I'm really glad for the conversation on education, in part because as a non-technical person, this has been the only part of the program I've actually followed today, so that was good. But being still fairly new to this field, what I've noticed about electrochemistry is the things that you guys are discussing here, it doesn't have that base home that so many other disciplines do. And so I just throw it out there, Tom, really to your point about creating curriculum that could span across universities. As a convener of this community, ECS is in a great position to help with that. This is something that our education committee is very committed to. We've looked at really expanding beyond what we're doing. What we need are people to help. So as we have a room full of electrochemists and people that understand this and the importance of this, Shannon Reed is our Director of Community Engagement. He's in the back of the room. We'll be here the rest of the day today, all day tomorrow. So if you're interested in getting involved in creating curriculum that would do just what we're talking about, we'd be very happy to talk to you. We'll be here, like I said, all day tomorrow. So thanks very much.
Awesome. Veronica?
Yes, so to the topic of diversity in electrochemistry, I just wanted to add the dimension of kind of the global reach and the global passion for electrochemistry that is really developing. At NC State, I have a collaboration with African universities called SciBridge, where we're really capitalizing on the tremendous interest in universities in Africa in renewable energy to help them kind of have hands-on experiments in this area. So we have teams of students at NC State right now developing these low-cost potentiates that Jeffrey mentioned. And I think the development of open source courseware supported by professional societies like ECS would be wonderful for this global interest. And I think we should all be interested about what happens to energy development in developing nations, as in sub-Saharan Africa, because they are developing their energy grids as we speak. And wouldn't it be wonderful if those developments included the scientists and engineers that are being trained in those countries? And there are many of them, and they are very interested and very passionate. This December, the African Materials Research Society is meeting in Tanzania, and Jennifer Rappe from MIT is running an electrochemistry workshop there, also organized by Susina Haile. So I just want to add that global dimension, that global interest in electrochemistry that I think is really wonderful, and I hope the kinds of things we're talking about here will have that reached to regions there too.
I just want to second that. I can't say that enough. You know, the axes by which I look at the world is on one axis is state of economic development, and the other axis, when I'm thinking about sustainable technologies, the other axis is light duty and heavy duty. And the only way we're going to solve global energy challenges if we attack all four quadrants. And there are billions of people out there that are living on a few dollars a day, and they're growing, and they have needs. And then, you know, a Model 3 is now it's affordable, not for more than half the planet, right? I mean, it's a totally different set of boundary conditions, a totally different ecosystem. Engagement is essential, but also I want to make sure that our students in this country and other developed nations are thinking about global solutions, not just let's solve the problems in the Bay Area. Thank you.
Deborah?
So I've not been in academics for 30, 40 years. My career has been in a U.S. military laboratory. And I noticed sort of circa Cara Bessel's time as a postdoc that if you start to integrate high school and undergraduate students into team research, it changes their perceptions of what they can do in science and engineering. And as valuable as these summer experiences are, we have found it's invaluable to have an undergraduate spend 6 to 12 months of full-time research with our team. And we often go for the high B students. And this gets a little bit to Tom's point that if you can get the students who may not be the usual suspects in, it totally changes their perspective of what they can do. They understand that, yes, you can do great exploratory, innovative work, and that gives them the will to persist through all the masochistic crap. And after we teach them to, do good lab work, trust their data, do it safely, and they start feeling comfortable with our team, which is multiple PhD staff and postdocs, they will then say, oh, now I see where I'm getting that crap in class. And then they go back and start acing everything. But if you give them 6 to 12 months, they recognize they are scientists. As we like to say, they work with us, not for us. Language is important. And they go on and win, major co-op awards at Alfred University or get NSF graduate fellowships because they then take ownership of their scientific career. And those are the people you want to walk into your graduate programs, not let's get them up to speed once they've gone to graduate school. But the other huge advantage is bright, curious, adventurous undergrad, totally cynical, jaded, burned out postdoc, even the ones that have come out of good departments, and you can just see the energy transfer. Postdoc gets the will to live back.
Some really excellent points here. And yeah, please, if you want to introduce yourself, or anyone who gets up, if you can introduce yourself.
I'm David Rosidi. I'm from NIST postdoc. I'd like to second that point. As someone from like a small town, Smyrna, Delaware, I found my career kind of happening by chance. And I think there needs to be a solid emphasis on getting them while they're young. And I've heard a lot of people talking about efforts in undergrad, but I do think there needs to be a bit more in terms of the high schoolers and making sure to grab them when they have that spark before they end up somewhere where, it's kind of obsolete at that point. They can't really get into the realm that we're in now. So I just wanted to say that I back her up on that.
Thank you.
Yeah, to the point of the sort of global reach and idea of open source materials, like a very short plug, I'm currently involved in the early to perhaps middle stages of developing an open source electrochemistry textbook. So we're also potentially looking for a few guest contributors in various sections. So if anybody's interested in hearing more about that or potentially being involved, feel free to come find me and I can perhaps plug you into that.
Can you just introduce yourself so we know?
Oh, sorry. My name's Rachel Kirchen. I'm a postdoc at Carnegie Mellon.
Thanks.
And she's from our Energy Frontier Research Center initially, I'll just state.
There was a whole list of questions here, but in thinking about this, really the only question that matters is the one we're talking about. I think all of the other questions really, if we don't get this right as a community, it's pretty much, going to be here 20 years from now saying, well, what happened? So we don't have to cover all these questions, and I think the education component is really the only one that matters, and we have some really important action items that have come out as a consequence of this discussion that we can all follow up on. So we don't need to rush to the next topic. If there are more folks, maybe some online, anyone who wants to point out something of what we can do better and how we can further education, what we can learn from other countries and regions, please, we have ample time to do that. There's no need to go through these other questions because this looks to be the most important topic.
It's interesting. We heard a bunch about this, about early exposure, about awareness, about context, and about training. And some of that sequence is probably different for different people. But I think one of the issues with electrochemistry historically has probably been is you grab Bard and Faulkner, and you have to go learn that, and then you can go do electrochemistry when we know we can now do just the opposite. We can get people engaged in electrochemical things and then have them have more the desire and the context to learn that. So a lot of the examples we heard today, I think, were a lot about context and not trying to go too rigorous with too much training before you have the context, and the impact, I think, is important.
And I also think we can all help each other out in brainstorming. In many undergraduate laboratories, there may or may not, but there may be an electrochemistry portion, and we could help brainstorm ideas to take the basic cyclic voltammetry experiment and make it into an experiential learning platform on which students can actually contribute to new knowledge and take that contribution and go out and tell their peers about it as well.
So I'd like to say that for our students to be better prepared at the undergraduate level for electrochemistry, there are many things I'd like them to be exposed to that they would have no way of seeing such as just the engineering perspective. You know, I think all science undergraduates would benefit greatly from having 1 or 2 engineering courses. Just the platform of reality that this brings to the discipline. But we're always under pressure. If we add another course, what will we take away? You know? And so the quantization of courses into semester-long, if you want to say 12 credit units or 1 CU, however you count, I think it would be interesting to think about a science education in modules and say, what if you only took 8 of the 10 modules of organic chemistry? Might that be enough and you could sneak in something else? What if you took 6 of the 10 modules of physical chemistry and 4 of the 10 modules of inorganic chemistry, but then you had room for, you know, some exposure to dielectric materials or smart materials, or you had some exposure to transport, you know. You talked about the University of the Future. I see a lot more mixing and matching rather than drawing up another degree program. I think the idea that all the students are closer to free agents and they can take a basket of valuable things and declare that to be a college education, I'm not sure I have that totally worked out, but I think we're going in that direction because people have many different goals, and electrochemistry is one very valuable, highly interdisciplinary goal, and we will need to be able to go and access many skills, but you'll have to leave other things to the side, and there's only so much time to acquire this knowledge.
I just wanted to add a point to that, and you know, in this dialogue that we're having about the University of the Future and exactly the basket of, you know, what makes an education, the difference between what we're talking about here with electrochemistry and what the typical conversation is the typical conversation is kind of a restructuring of things that already exist, and I think we've already identified that we are lacking in more rigorous training in electrochemistry, and the point is, there's only one place to go, and that's north, right? It's up. The vector can only go in one direction. The question is, what's the steepness of that vector? And that's for us to decide as a community. In other words, anything we create is going to be better than what is already out there. We have a clear opportunity, whereas in the other dialogues that are happening, it's like, oh, but we're going to lose out on this and we're going to lose out on that if we reshape. We can only win by doing something differently than we're doing today. So that's the opportunity.
I think your point before, Tom, was a really good one in that all these areas are siloed but amenable to sort of infestation with electrochemical theory. You know, for instance, from an organic standpoint, I don't think there'd be any organic chemistry professors out there who would be super upset if an electrochemist said, well, why are you not infusing more electrochemical thought into, we teach redox reactions, and the easiest way to explain to someone a redox reaction is kind of electrochemical, but at least when I took organic chemistry, there was actually, at NYU, there was 0 electrochemistry in there at all. So I think all the other courses probably wouldn't have any problem with that either. So it's probably, as you said, the shovel-ready idea is, I think, one that's easily instituted pretty rapidly. Yes?
Mark Jones from Dow Chemical. So I'm a person who for 30 years has been hiring people. And I found your talk, Phil, to be really inspiring because you weren't selling yourself as an electrochemist. You were selling electrochemistry as a tool to solve your problems. And I think the aspirational goals that I'm not hearing said in this are you want that to happen with electrochem. I had reason to look back at the history of GC and mass spec. And mass spec at one point was itself a discipline. People were learning how to build equipment, and the equipment. Over my career, they've become commoditized. I think that your aspirational goal should be the commoditization of electrochem such that any random organic chemist can grab it when it's the right tool.
Yeah, that definitely much better than what I said during my talk. That's great. That's great. Absolutely, yeah. Great. That's a great point. So are there any other things we want to discuss on the education front, or we have about 25 minutes remaining. Oh, yeah, someone else is.
Hi, sorry, I'll make this brief. I'm Alex. I'm from Pine Research Instrumentation. So when I was a graduate student, one thing that I did was STEM education, outreach, things like that. I think the NSF also has, like, part of a grant proposal is some kind of broader impact, things like that. And I would say the best thing that I did, and if we're thinking about the idea of educating future generations, High school is good. It's around middle school that's when students start to get the belief that like they either can or can't do something. And in particular, I was more interested in STEM outreach programs. That it wasn't just like, oh, we're going to have a thing like once a year. It was a regular mentorship program that met on like a monthly basis, taught by graduate students actually, and specifically for like at-risk students. It's like if you want to have diversity, you need to target at-risk students, not just of different racial backgrounds, but of socioeconomic backgrounds as well. And one thing I will say, if you want to just improve just graduate education, like having graduate students teach middle school students is really good. Like some of these kids have never heard like what's a plot, like, and it really gets the graduate student to think very deeply. Like I learned so much from teaching middle school students about science, like almost more than I did in graduate school. Like I learned a lot of detailed stuff in graduate school, but like fundamental science about like what's a hypothesis and things like that, like explaining that, like when a graduate student is forced to teach something, like that's how they really learn it. And if you could have more programs like that so all I want to add is that like if you want to do more education, more STEM related stuff for future generations, those are just a few thoughts for the panel.
So really good points. Many of us spend a lot of time, Shelley, on writing those parts of NSF grants, and this seems like a great action item we can all take into consideration. So yeah, thank you for that. So the equipment question I asked seemed rather boring. So what I'm going to do is like go fishing and see if there's a topic which stimulates this level of lively discussion. And maybe in the final 20 to 20... Oh, great. We have another... Yeah, sure. Any topic you like. Yeah.
No, Phil, this is... My dream equipment is X-ray eyes underwater. Okay? That's what I want. I want X-ray... Everything we have right now is, vibrational spectroscopy, variety. Scanning probes. We've got ex situ capabilities in UHV, subject to all kinds of drying and so on processes. Then in situ, in aquo, in under operando conditions and so on. That's what I want. And I want spatial resolution, angstrom level. I want chemical resolution, not just like 20 years from now. And I want to be able to look at the processes at video frame rates. If you couple it to photochemistry, I want to have pump probe capabilities and femtosecond time resolution, and we don't have it. This is like we're looking at these interfaces from a perspective of 1960, and that
everything's
really hasn't
indirect.
changed.
You want something more direct. Then that aspirational goal might sound blue sky at the moment, but that's really I think what the equipment question was about, was exactly that type of contribution. So if you have that kind of far-reaching blue sky type of dream, I mean, that could be the basis of someone's proposal or tenure or Holy Grail aspiration. So thank you for that. But if there,
I would to jump to your question.
Sure.
I think that there's been some discussion, but I don't know where they'll get codified by the end of tomorrow. There's some pretty major challenges out there to move this field forward. The nexus of biology and electrochemistry. There's some practitioners like Shelley that are very well aware of it. There's a whole other sets of problems there. Where does synthetic biology meet the electric economy? Where do we think about doing electrochemistry in brackish water? Why do we have to have really clean water? How do we deal with all the counter ions? If we're going to grab CO2, we want to grab it out of the seawater instead of out of the air. How do we do something there? How do we use both sides, both products from both electrodes? There are very few places where we're actually adding value at both electrodes. I think that there's a lot of those things that are, I think, cut across a lot of the different areas we've heard. And I'm worried if we don't capture a few of those challenges, they might not get captured elsewhere. I don't know if people just have a set of challenges they're interested in. I mean, this idea of electrocapacitively purifying water and doing energy storage at the same time as you build up charge. I mean, thinking about these hybrid approaches, whether they're abiotic and biotic or storage and moving things around, I think there's a lot of opportunities there for us to think about. And I was glad, I was fascinated. I grew up an organic chemist. I'm glad you organic chemists have already figured out electrochemistry, because some of us have real problems we still have to figure out.
It's a great point, Bill, and it gets to the question of, manufacturing and these kind of large-scale questions. And, before we switch to that, there's already two people standing, so, let's hear from the audience.
Ladies.
Lindsay Seitz, Northwestern University. I also want... Is this on? No.
It's not on.
I think it is. All right. I also want all of those in situ and operando tools, and I'm trying to work on them, but I also want to understand what exactly the effect of the perturbation of each of these operando tools is on the system. I'm sick of spending 85% of my beam times trying to understand the degradation mechanisms that I'm bringing in by adding extra photons to my system, and only getting to talk about the exciting operando experiment at the end. And 85% of that stuff went buried in the supplemental that nobody will ever read. But I think that's incredibly important to helping us understand the fundamentals of these electrochemical systems, is the fundamentals of the interactions with these characterization techniques.
Thank you, Lindsay. This was exactly the preamble for my statement that actually derives from Esther Takeuchi's lecture on the importance of bridging scales and the importance of adding temporal resolution. We also need to add the chemical resolution to those techniques. People are using these very strange English language expressions, 4D, 5D analysis. I live in 3 dimensions, and adding time is okay, and adding chemical composition is okay. I don't need to call it 7D or something. So now, there are 2 very dramatically different needs, I think. There are domains of needs. One domain of need has to do with the centralized equipment. Let's call them synchrotron needs. In the synchrotron needs, the more complex lines, the lines which have more multi-tools and tools with a higher and coherent temporal and spatial resolutions placed on the line. In order to compete with the rest of the world, we need to have that 127-meter line as in Spring 8 with 11 instruments on it, designed by the Tokyo Telecommunications University. I go there and I spent 2 hours just walking around those instruments. They're amazing. How we're not blown out of the water is because they're peculiar and slow, and because there is no train station to take on to go to Spring 8. ESRF is coming out after a substantial overhaul. It will become better than Brookhaven in 1 year. This is a race, and this is a national race. We cannot win this race with buying better and better equipment and writing MRI proposals, because our MRI purchased equipment, thank you NSF, they become antiquated by the time we install them and bring them to full. The national investment in complex, centralized, light sources and associated, also of course, neutron sources and the like is critical for us to be ahead of the game. And the second thing is about the unique equipment at the upper level at the universities. It's critically important to amass effort to build institutes or establishments of a critical microscopy and spectroscopy equipment that has electrochemical cells or electrochemical plugins, like assistant professors who will dedicate their tenure to the insert, like you. Okay, but we need 17 of those, because there will be not a single one cell that will be the in situ cell for electrochemistry. There will be 12 different in situ cells for different types of electrochemistry. And that investment, it's a large ticket. It's almost as large as everything else that we do. It's not pickable today by the industry, and that's why I'm voicing this DOD, DOE, NSF, whoever philanthropy call for investment in that. Because before we go to these Pfizer's or whatever, that is a light cavalry. The tools for that can be self-invested out of the profits. The tools that I'm talking about are a national investment. This is like a space program. We definitely need it. Thank you.
If I could just add one thing to that, too. These are great comments. One part that is very important for all that to work is the data processing and analysis, and that's also a skill set that my personal bottleneck and our group's bottleneck at the Beamlines. We work with amazing people that help us get these experiments going. We capture great data, but it's not quite information yet, and it's definitely not knowledge yet. And that requires people who are dedicated to do the modeling, and it's very sophisticated and it's very challenging, and there are frontiers to be pushed there. And I'm seeing that as, you know, and I don't think we have enough human power resource as it is, but we have much better on the experimental side than on the support on the simulation and theory side for those types of experiments as well. And that has to go hand in hand, otherwise we find ourselves in a bottleneck. That's true.
Let me, we have 15 minutes, and so let me just throw out something that might lead to some discussion on the manufacturing topic. You know, when we heard some amazing talks this morning, and we'll hear some more tomorrow about these amazing next generation techniques that could be out there for hydrogen or ammonia or whatever. And so what do you think are the largest roadblocks to getting this to be accepted and used by industry? We have industrial colleagues in the audience can talk about this. Is it because of the sort of conservative nature of processes that already work, or what are some of the roadblocks that you're having within academia or within industry on this topic?
I wanted to say one small thing. I think that in the area of photovoltaics, for good or for ill, there are very well-defined metrics and benchmarks. There are standardized conditions under which they have to operate. There's durability guidelines and safety guidelines, and efficiency is a metric that is curated by a national laboratory. To my knowledge, in electrochemistry, there are a variety of performance metrics we might like to get to, but then we might sacrifice on other areas. And even just reading the papers and comparing them, it's difficult to really discern whether a breakthrough is ahead of all the previous work because it's such a multidimensional space. You know, when they evaluate football players, now they have this sort of star chart, you know, how tall you are, how fast you are, you know, your wingspan, how you catch a ball. And I feel like electrochemistry, we need that kind of a chart where at least we could have a side-by-side comparison, even if it's somewhat more complex than the case of the photovoltaics. And that's a challenge to my colleagues.
So one comment I wanted to make is the opportunity, and I think it is an opportunity to facilitate interaction among national labs, universities, and companies or industry. That I think, you know, I was impressed, Phil, with your talk earlier today because you were clearly able to bring in a lot of industrial participants. But I have to say that the infrastructure that we have right now, I would say is a real detriment to that. Just the amount of documentation and paperwork and agreements. And, you know, by the time you get through all of that, whatever question existed has either been solved or the company went bankrupt, you know. So I think if there are ways to facilitate interaction among people who are doing really fundamental science and those, you know, and academics and people who would be in a position to adopt that technology would really help address some, not all, but some of these issues so that information transfer could be facilitated.
So I think going back to industry, I want to build on Andrew's piece a little bit. You know, whether it's microelectronics, hamburgers, photovoltaics, or jet planes, there are these learning experience curves. And 2005, the Office of Science, Basic Energy Science, Basic Research Needs for Solar Energy had an experience curve in the fundamental needs for solar energy. And I think getting that mindset, or what are the important metrics, Are we really tracking them, and where does innovation help you go down that curve? And I've been trying to find one for electrochemistry, and there's a few out there, but since 2005, that thing's kind of been indoctrinated even into really fundamental solar energy people who have just watched that learning curve. And solar was over $10 a watt in 2005 at the basic research needs, and it's way below $1 a watt now. And so I think thinking about what does it take to industrialize some of these things and asking ourselves, how much better do we need to be in efficiency? How much better do we need to be in other performance? Or where does the manufacturability come in? The other big one, and you made me think about it when you talked about kind of putting the big iron together, CapEx is still a big issue here. And thinking about lower CapEx is really important. Tom alluded to it, but some of the upfront hardware costs on some of these systems, not just the electrolyzers, but the balance of plant, are huge. And so innovations across that spectrum, I think, are critical.
Yes, from Dow.
I don't have a flak jacket, so be nice. So I work at Dow Chemical, which until 2 years ago was the largest practitioner of electrochem in the world. And my apologies to anyone from the Electrochem Society, because much as I tried to keep Dow in the Electrochem Society, where Herb Dow was a founding member, I was unable to find enough electrochemists that cared inside the company to even do that. So the reason that it is a tough sell to do electrochem in industry comes down to scale and the cost of electrons in general. I have made 7 runs at electrochem processes over 30 years, succeeded 0. And it always comes down to, if you can do it with heat and beat, it always wins. And that may be changing as we talk about moving to electrification, wanting to get rid of CO2. But inevitably, it comes down to the dependence on scale and capital. Scale beats experience curves every time, and that tends to be the killer. So chlor-alkali, if you look at the experience curve, it flattened out because we couldn't make the cells any bigger, fundamentally. And Dow ran the biggest cells in the industry. So that's kind of where it comes down to. Again, where you're going, where you're doing something that you can't do by heat and beat, that will always win.
Yeah, thanks so much for that. And then Bill made some really good points. And I know Jake had a question. I wanted to get to him. And he actually reminded me, because as a novice, when I read the literature, like I noticed there was studies towards making ammonia electrochemically. And then Tom pointed out some really important features about that this morning, that it may not be all it's cracked up to be. And we actually included it in a review. And it was still in the early view. And Jake Guested emailed me and said, are you sure about that ammonia stuff? And so I looked into it. We ultimately removed it from the final version of the review because we couldn't really find much, in some things in the dark web about it, but really couldn't find much in the way of verification of it. And, you look at these things like battery technologies, and then you hear Elon Musk talk in the shareholders meeting. He's like, oh, we tried everything. Most of the academics in the battery chemistry, it's not real. And so there really needs to be better communication between the literature and the academics and the actual industrial people who know what's going on. I know Jake had a question. Yeah.
Yeah, that was basically my question. Not in so many words, but just to pick up on what Andrew said. One of the things that is difficult for me as an editor is that I feel like the academic literature in electrochemistry is, if anything, over-metricized. Right, and so it's subject to basically, there's 3 or 4 parameters that people really fixate on, right? What's the overpotential? What's the Faradaic efficiency? What's the durability of the catalyst, right? And it seems to me that, and then they make this big table and they say, in 2 of these 3, our catalyst is the best relative to the 20 or so that we're citing here, right? But that doesn't actually tell you whether it's good enough for the particular application that you're trying to achieve. And so, I sometimes wonder if the field is in some sense too tied to metrics for their own sake, at the expense of trying to figure out what's good enough for a particular process that you're targeting, as opposed to sort of more generic accomplishment across the board. I'm wondering if anyone could comment on that.
Yeah, this is a great point, Jake. Yeah, I mean, I think, just to give it from the example, one of the examples that I gave today on hydrogen, for instance, right now, if you're an electrolyzer company selling acid-based electrolyzers, you're not willing to pay an extra millivolt right now. And the question is, will that future change? And you can come up with a hydrogen and let me say in catalysis, these are orders of magnitude effects, right? A good catalyst and a bad catalyst are 10 orders of magnitude apart. And so the best non-precious metal systems are at least 5 orders of magnitude worse than platinum. And so if you make one that's an order of magnitude better than the state of the art today, you're still 4 orders of magnitude away from platinum. And that's really to the point that you're making. But now to address that doesn't mean it's not useful, for sure. And it comes down to techno-economics. It's OPEX, it's CAPEX. What does the full system look like? Can you design your electrolyzer differently? Electrolyzer companies and fuel cell companies work so hard to minimize precious metals. They put so much fabrication costs so they can have as few micrograms as possible. If you had a totally free catalyst by comparison, you can come up with a different electrode design. And maybe you win because now you have better mass transport because you have a whole lot more. Maybe you can put 2 orders of magnitude more sites and design things differently. So it just opens up design criteria. And I think what I'm trying to get at here is that there's not enough work out there that really looks at the big picture. And I think that behooves all of us to try to put into context the bigger framework, and to do that not just in this very simple example of water electrolysis, but how do you compare that to other technologies that make hydrogen so that you can say, who has a chance at heat and beat SMR? Right. So I agree with you. Your point is something we should all be thinking about.
I don't want to lose the beginning part, and I thought that was very observant. Let's not lose fact on the storage. We know where curtailments are happening today because we can't store enough renewable energy. We know that we can't take today's lithium-ion batteries and probably store terawatt hours of energy. We know that probably the chemistry needed for the car isn't necessarily the chemistry even needed in batteries for grid storage, which has very different performance criteria. We know we can store a lot more electrons in covalent bonds of molecules, but we also know there are things called reaction barriers or overpotentials or round-trip efficiency issues pulling those out. But there are some things, if we're going to put massive amounts of renewables on the grid, for example, we're going to have to do storage, or we're going to have to do it at very large scales, at multiple scales, and we're going to have to do it differently than we do it today, in addition to using what we know today to make that transition.
Yes.
Okay. Hi, I'm Kat Stefan. I'm an editor at Joule, and I wanted to jump off of what Jake was saying and say that, we're really open as journals to having these discussions with the community, with thinking about like what are appropriate metrics? Are we even reporting things properly? Are we performing the correct measurements? With, the isotope labeling of ammonia production is a really great example. And I think, if these are things you're concerned about, talk to us about them as well, because we're thinking about what we can do from our side, because we're publishing literature and we want that literature to be helpful and accurate and repeatable and reflect the community's needs. And so, just as an invitation to talk to us, because we are thinking about these problems as well. And I think it's a really great discussion that we're having about that.
Fantastic. Thank you.
I'm Bruce Garrett. I'm from Basic Energy Sciences and DOE. Just getting back to Jake's comment about, metrics. From our point of view, it doesn't matter whether you're beating a metric or not. It's really what you're learning about the fundamental mechanisms that underlie that, right? That will ultimately lead to improved systems. So in terms of what gets published, that's the kind of thing that we want to fund, right? So I think I just wanted to make that point. I don't care so much about the metrics. It's really the understanding.
Fantastic. Well, I am a terrible failure as a moderator, and Ellen will never invite me again for such a job. I'm quite certain of that. But we have reached the time limit here. So if there are perhaps one of the experts in the panel who we are eternally indebted to for sharing their wisdom with us today might want to give some closing remarks that we can look back 20 years, because it's all on video, 20 years from now, and look back and say, well, that was quite a premonition they had. So any takers? It looks like I knew Bill would do it.
No, I was waiting my requisite X seconds. The world's going to electrify, guys, and we're going to have to be much better converting solar and wind energy into electrical energy and interconverting that into chemical energy and eventually even dealing with the thermal energy side. And I think this energy interconversion is going to be here for a long time. We've heard all sorts of other applications that make perfect sense and all sorts of benefits to society way beyond energy. But in addition, the world's going to electrify, and we're going to need to figure out as a nation where we're going to play in that ecosystem.
Well, on that note, let's. Yeah.
I just also want to add to that, just to keep creatively pursuing new knowledge. I mean, science is beautiful. We have the best jobs, right? Because we're entrusted by society to find new knowledge. So don't follow recipes and think outside of the box.
Great advice for us all. So please join me in thanking the panel for their time today.